Good morning, good afternoon. It is a pleasure for me today to introduce the eWaste Challenge MOOC and the presentation that Karel Van Acker from KU Leuven will give later on is included in the context of this massive open online course that is available since April and will remain available as e-learning for a long time. As mentioned by Dan, my name is Francesca Ceni. I'm a program officer in the BRS Secretariat, and I will introduce the context of the lecture today. This massive open online course on the eWaste Challenge has been developed as a result of a partnership between the European Union Institute of Innovation and Technology, the Climate KIC, and the Basel, Rotterdam and Stockholm Conventions Secretariat, KU Leuven, and the World Resources Forum. A new partner just joined the adventure. It is the Raw Materials KIC, and this partner will be part of the MOOC and take the MOOC forward in other universities. The MOOC is being developed for a broad audience, for example, e-waste recycling managers, urban planners, graduate students in engineering or in environmental management, and recycling operators. So the MOOC is accessible to all, but provides enough depth and further resources for anyone who wishes to dig deeper into the topics covered. It requires 30 or 40 hours of learning, and this is divided in short lessons that we call learning nuggets, grouped in 5 modules. And each nugget has a discussion thread and a forum where the learners can exchange ideas and discuss with a moderator. People using the MOOC can complete it at their own time, and they can choose the subjects and the order in which they follow the subject. Their learning is activity-based, and it is designed to support the main challenge. We'll see later what the challenge is. The MOOC is hosted by the Innovation Primer. It is a platform of the Climate KIC, where you may also find other MOOCs that this consortium of universities has developed on climate change. As mentioned, the learning is grouped in 5 modules, and the lecture of today belongs to the 3rd module on managing e-waste for a greener future, where you will see good and bad practices, but also innovations for e-waste management and also for e-waste prevention. The MOOC will offer a learning community, as mentioned, and it is designed to support the main challenge. The challenge will take people to half the price, so the certificate. In order to obtain a certificate, it is necessary to submit a project, an idea, an improvement, innovation, a campaign, a community initiative, or a research project, or a business idea. This challenge should have the potential to have a positive impact on environment and health, and should help to prevent human-made climate change. Each module of the MOOC supports the development of a challenge in the specific area of the module. So the learners can choose the subject among the modules and the nuggets which are proposed in the MOOC. As mentioned, the learners will find discussion forums and groups. So join us for this adventure and go to this link and connect to the MOOC. As mentioned, the MOOC will remain available for 8 weeks. There are webinars, interactive lectures for the learners, but after that, the MOOC will be available as e-learning. I want to mention again that there is a new partner in this adventure, the EIT Raw Materials Kick, which is not linked here, but it will be linked soon. Thank you, and now I pass the floor to Dan.
Hello to everybody. My name is Karel van Akker. I'm working at KU Leuven in Belgium, near to Brussels. And I have the honor to present you this webinar on sustainable metals and recovery of them and regaining the value of those metals and other valuable materials out of e-waste. So first of all, I would like to deal with the question, what do I exactly mean with sustainable metals? What are they, and why should we be concerned about sustainable metals? And then the main topic of this webinar will be how can we find them in e-waste, and how can we recover them, and how could we better recover them than the current situation. And I will end the talk with presenting you 7 challenges in metals recycling from e-waste. So, metals are actually very valuable, and there are some reasons for that. And the first reason is that the natural resource base from which we extract metals degrades over time. The problem is not that metals are scarce in itself, but it's rather that the ores from which we extract metals are becoming more and more poor, let's say. They contain less metals. The rich ores are already mined and already exploited. So we can see that in the early 1900s, for example, for copper on this curve, the percentage of copper in ores we could extract was 3%. Today, we reach about 0.3%. That means that it is a factor 10 less copper that we can extract from the same amount of ores. And that also means that we need 10 times more or less, 10 times more energy, that the impact on the environment is much higher, and so on. The second reason why metals are valuable is that some of them, and especially those that are used for electronics, are what we call structurally scarce. That means that quite a lot of these metals are linked, are found together with other metals. We call them then carrier metals in ores. For example, indium, that's an element that is used for mobile phones or for tablets in the screens. That indium, we find that together with zinc in ores, but if we have 3% zinc in an ore, we only have 10 ppm indium in that same ore. And so it's a ratio of 1 to 3,000 more or less. That means that the amount of indium that will be brought to the market is completely depending on the amount of zinc, and it will not increase, we cannot increase as such the amount of indium on the market, since no company will increase the amount of zinc brought to the market. So it's structurally linked to the situation of zinc. The third reason why metals are valuable is that their resources are not well spread over the world, but are concentrated in a few parts of the world. and yeah, some of these elements are very concentrated. For example, antimony is produced for 87% in China. The same holds for rare earth elements. They can be found in other parts of the world, but the market situation is such that there is a quasi-monopoly on the delivery, the supply of these metals in some countries, let's say. And that's the reason why, for example, the European Commission, and similar things happens in the United States, they define or they make a list of critical metals, critical materials. And criticality is defined then as the importance of these elements for the economy versus the risk of supply of these elements. So the higher in this graph, the higher the risk of supply, and the further to the right, the more important these elements are for the economy. And so all these in this red square, all these elements are called critical since they are important, but the risk of supply is very high. And we see that in that corner there are especially elements that are important for electronics and that we will find in e-waste today and in the future. For example, we have the rare earth elements that are used for wind energy, e-mobility, compact fluorescent lamps. We have germanium, indium, gallium elements that are used for solar energy, solar panels. We have cobalt used in batteries, and so on. And finally, it's not only about the supply and the risk of supply of metals, it's also about the impact they have on the environment. And they do have an impact during mining, during production, during use, and during wasting these metals. So there is actually a very clear link between metals usage and production and the energy and climate crisis. We know that 25% of the worldwide greenhouse gas emissions is linked to the production of materials. And a part of that, a quarter of it, for example, is then linked to the production and the use of steel. So there is an important linkage. As you know, there are also health effects. There are risks of calamities in mining, such as this picture shows you that the inundation of red mud in Hungary in 2012 that we had. Okay, so I hope that these slides have shown you what we mean with the value of metals, why they are valuable, not only because of the price on the market, but mainly because of their externalities, and so their scarcity, their impact on the environment, and so on. And that's why we move more and more towards what is called sustainable materials management, or today, especially in Europe, we talk more and more about circular economy, which actually deals with the development of new technologies and new business models for keeping the added value of the resources and materials as long as possible in the economy, and this also by eliminating waste, since waste actually is a real loss of value. It's weird. It's maybe, if I may use a strong word, it's actually a scandal that we waste all efforts we have done in extracting metals, in making products, and that we wasted after a few years of usage. And at the same time, this new paradigm is also about minimizing the environmental impact of material loops all over the system of in which these materials are used. So keeping the added value of those materials is about keeping the quantity of these materials available for new products, but as well as keeping the quality of these metals and materials after they have been used, keeping that quality as high as possible. And some strategies to realize this circular economy or to realize sustainable materials management is, in very short here, is to, first of all, to improve their renewability. That means that we want to use these materials, these metals again and again. They are used in a product. After that product is wasted, we want to reuse them, to recycle them. We want, in other words, to close material loops. A second strategy is to dematerialize. That means that we want to to do more with less. That means that we would like to develop products and to use products longer, that they have a longer lifetime, that they are used more intensively by sharing, for example, but also that we increase the efficiency of our materials use, that we make products with the same function in which less materials are used or wasted during production. And the third strategy is to substitute critical metals by less critical metals, to use alternatives for that. And whatever strategy we follow, whatever solution we invent to deal in a more sustainable way with metals, we always have to check whether it's positive with respect to the whole life cycle in which these materials are used. But today I will focus on the first strategy to improve the renewability, and in other words, that is dealing with the recovery by closing material loops, the recycling of materials, the recovery of materials, or as well dealing with the design for recycling, and so that we make products that are made to be easier recycled after their end of life. So if we come now to electronic waste, we have all kinds of electronic products. We have the housing and mechanical parts in which elements are metals are used. We have the electrical parts, we have the electronic parts. But in a study we have conducted last year, again we have seen that that critical raw materials, that are the CRMs, are mainly found into electronic components attached to the printed circuit boards. And for this type of printed circuit boards, you see here a typical composition and in weight. So you have quite a lot of aluminum oxide and silicon dioxide, but you also have silver. You do have, for example, copper, of course, nickel, cobalt, iron, but also you have gold, and that's the composition in weight, of course. And if we want to recycle, then we see today that recycling activities are mainly focused on the recycling of those precious metals, the gold, the silver, the palladium included in electronic waste. And the reason for that is quite simple. If we look at the concentration of those elements in what we call the urban mine, so the waste of, for example, cell phones, the waste of catalysis, the waste of PC motherboards, we see that the concentration, for example, in a motherboard is for gold 200 grams per ton. If you compare that with the composition of of gold in ores, in primary mining, we only find 5 grams per ton. So we find 40 times more gold concentrated in motherboards than we find in ore. So the concentration is higher, the grade is higher if we consider motherboards as a source for the recovery of gold. Of course, we have to bring all these motherboards together. That's another issue, that's another problem. The recycling scheme is quite complex. If we focus for a while on computers, sorry for this. I hope you still hear me well. So the recycling scheme for computers, for example, is quite complex. We start off with the collection and the sorting of computers and their components. We dismantle them. We do some mechanical separation. And in the end processing, the different parts go to different recycling facilities. Iron and steel parts are going to an iron and steel plant. Aluminium is going to a non-ferrous metals recycling. And if we look at a printed circuit board recycling, it goes to mainly, if we look at the high-end technology, they are going to an integrated smelter, and there are a few companies in the world having that, for which we can extract them on gold, silver, palladium, and so on. We did some analysis on that. Where are all these parts going to? And for laptops, here we did the analysis actually for Flanders, that's the northern region of Belgium. We did the analysis of a number of laptops, and the average composition is shown here. So it's more than 14% iron, 8% aluminium. Precious metals are actually only 0.03% of the total laptop, and so on. And after this recycling, this if we follow actually all these different recycling and processing recycling plants, then we see that from the total laptop, almost 12% is going to a steel plant, 2.3% is going to a copper plant, 10% to aluminium, and for example 18.5% is going to the integrated smelter, which is specifically designed for the recovery of these precious metals. And you have other end processing facilities as well. Please also note that 22% almost is still going to a landfill. And I have to say that this scheme in Flanders is actually very well developed, but still here 22% is directly going to the landfill. If we go into more detail for the recovery of those precious metals, a typical scheme, which I will not explain in all details now, for such an integrated smelter is shown here. What is important is that at the end of these processes, we can actually recover at the bottom, we can recover 17 different elements from the input into this integrated smelter. So typically input is are the motherboards of computers or cell phones and so on. So there are several metallurgical processes included, pyrometallurgy, hydrometallurgy, and so on. And the efficiency of such an integrated smelter is actually very high. For example, for gold, we can recover 95% of the gold that was included in the input, which is very good, of course. Also, the environmental impact is quite small of such a plant. But that is only the last step of the recycling value chain. Before we come to the end recovery, the end processing of this metal recycling, we still need the collection, the dismantling, the separation, and the pre-treatment. So if we looked at the green ones, and then we saw, for example, that if we consider all the copper that is included in a laptop, that almost 60% of that copper is going to the integrated smelter, but another 27% is going to the copper smelter, and more than 13% is included in particles that are landfills. So we lose actually 13% and more in these steps. And for the precious metals, it's even worse. We saw that 64% is going to this integrated smelter, and 36% is included in the streams that are going to the landfill. And why is that actually? Well, first of all, I wanted to show a more detailed table of numbers. So in the last column is the efficiency of this dismantling and pre-treatment step. And we see that the efficiency for iron is quite high. So 86% will be in a recycling proper recycling plant. For gold, although we had a 95% efficiency at the end processing, if we take also the pre-treatment and the dismantling into account, we only have an efficiency of 77%. So it's not true that we extract all the gold out of these computers. It's only 77% of the collected computers. Yeah. So why is that? It's not new. We confirmed by our study actually what is already seen in other studies, and that is that in the formal economy like we have in Europe, that we have high percentages of recovery of these valuable metals in the integrated smelter, but we have low, actually very low percentages of the separation, the pre-treatment of these components. And that's because of the automatization of these steps. What we do is we dismantle in some way our electronic equipment, but rapidly we are going to mechanical separation after shredding. So we are cutting these components into pieces. This shredding process is not very specific, so we get all types of combination of materials, and afterwards we try to separate, but of course you have plastic particles to which some copper is attached, and copper particles to which some gold is attached, and so on. So this separation is in an automated way is not very efficient. more efficient is when it is done manually, like we find in the informal economies. Okay, so far for the recovery and recycling of gold and silver and other precious metals, but apart from these precious metals, there is little information and little done actually in the recovery of other elements, especially other critical metals, as I have shown in that graph of the European Commission. And some of these critical elements are predominantly used in electronics. For example, gallium, 70% of the gallium is used in electronics, or indium, more than 80% is used in LCD, and so on. So these elements are very poorly recycled, and there is a lot of room for improvement. This slide, I will not go into detail, but this slide gives you an overview in which components we find all these metals. For example, tantalum we find in capacitors, or here at the bottom, rare earths, we find it in displays, in LEDs, in speaker audios, and so on. I will give some examples of these other critical elements. For example, the rare earths, which is very high on the risk of supply list. They are used to quite a high extent into the permanent magnets that are, for example, used in the hard disk drives of computers. So they contain, these magnets contain actually 0.6% rare earth elements. Also in mobile phones, they are used for the speakers. For these elements, they just end up in the slags, in the waste of the processes we discussed before. So new recycling routes are developed, are under development, such as hydrogen decryptation to break up these permanent magnets, or other types of metallurgy are under development. We need actually these new processes to recover such exotic elements, let's say. Another example is the tantalum we find in capacitors. 50 to 60% of tantalum is used in electronic components, and a lot of them in notebooks. And a single capacitor contains between 30 and 58% of tantalum oxides. So it's very concentrated in those components. If we can separate these components from the motherboards, we have a nice source, a quite pure source of tantalum. So that could help the recovery of this tantalum. Today, actually, the current practice is that they are not recycled, since they are just going to the integrated smelter together with these printed circuit boards, and they are lost actually in the slags. So they are not recycled at all in computers for the moment, in end-of-life computers. So if we could improve that recycling, what do we gain? We gain, of course, the availability of secondary resources. We also have to know and to realize that if we recycle, that also costs some energy, but the energy needed for recycling processes is often much less than for primary processing. That's shown in these graphs here. The blue bars are the energy needed actually to produce primary material out of ores, and the red ones, the red bars, show the energy needed to recycle materials. And for example, for aluminium, you see that the ratio is 1 to 10. And so you need 10 times less energy to recycle aluminium than to extract them for ores. For tantalum, it's very similar. for gold, it's even worse, palladium. So that's a very good reason to go for recycling of those metals. And of course, it's not only about energy. I only showed here energy, but it's also about water use in those processes, about other environmental impacts. If we want now to design components better so that they can be recycled better afterwards, we have to realize that not all metals are compatible with each other. So I already said that tantalum that is included in a copper waste stream is lost to the slags, and that holds for a lot of those elements. So important to realize is that not all combinations of metals can be recycled in a proper way, and that's expressed by this graph, by this metal wheel. So there are different processes included in that wheel. I pick one of these processes, the copper converter. What we see is that if we recover copper, we can also recover at the same time gold, platinum, and all the yellow elements here. But the white elements are actually lost in the slag phase. So if indium is included, or antimony is included, or germanium is included in the end processing of the copper, then they are lost in the slags. So it's important to realize that we lose these metals actually if we cannot separate them before this end processing step. So I come to the challenges to conclude. The first challenge is what I said just 1 second ago. We have first of all to improve actually the efficiency of separating components, separating metals mechanically before the end processing. The second challenge is that today legislation is mainly based on the recovery or on an amount of weight that we should recover from electronic waste, and an amount of weight of materials that we should recover. But weight is one measure, it's shown here, but the value of those materials included in electronics is another measure, and it shows a completely different picture. For example, the share of weight of gold in a mobile phone is only 0.03%, but the share of the value of gold in a mobile phone is 71%. So there should be more incentives actually for those value-based recovery instead of weight-based recovery. The third challenge is that more value in recycling can be gained when you recycle not separate elements, such as the neodymium out of a permanent magnet in a hard disk drive. But if you could recycle the alloys, so the alloy of the permanent magnets, and the neodymium iron boron alloy as an alloy, and then you can actually gain more value. The processes or the recycling circle is closer then. The fourth challenge is that we have to improve in the design of electronics the compatibility of these metals, as shown by that metal wheel. The fifth challenge is that something disappeared from this slide. I'm sorry for that. The fifth challenge is that today we think in that direction. We think starting from the materials, we want to recover gold from mobile phones, and how can we do that? Now, today we have to change to a product-centric view on recycling, starting from a mobile phone and thinking how we can recover every single material that is in there, so going in that direction. The sixth challenge is that companies and policymakers also want to know what waste, electronic waste, will come to the market. So the sixth challenge is to explore and predict the urban mine, and that's an example of neodymium, such a rare earth element. Where is it included? In what type of components is it included? And can we predict then when these components will come to the market? And for example, you see that neodymium included in automobile for electric mobility will only come to the market after 2025, for example. But that gives an idea when new recycling schemes should be ready to cover that. And the seventh challenge is a little bit aside from this webinar, but I wanted to conclude with that. The prices of those resources are extremely volatile, as you can see in these graphs at the bottom of the slide. And yeah, the policymakers should, by having the proper incentives for recycling, should counteract this volatility. For example, by stimulating recycling, by extended producer responsibility, since it's very difficult to open new recycling schemes when the price of the primary materials is going very rapidly up and down. So if the price is high, recycling becomes economically very interesting. But if it is very low, then it's again problematic. But a few months later, it's again very high, and so on. So with that, I would like to conclude my talk and hand it over again to Dan.